Hi, welcome back. So last time we looked at how to compute densities for functions of random variables or random vectors. And now we are going to apply that to relate beta and gamma distributions. And then we are going to go on to precisely state the Thompson sampling algorithm. Okay, so let me start by sharing screen. Okay, so today we are going to study the relation between beta and gamma distributions in this lecture. And I'm restating the lemma from last time, which we need to prove. And the lemma stated the following. So X and Y are independent gamma random variables with shape parameters alpha and beta, and a common scale parameter which we can take to be 1 without loss of generality. We define V to be this ratio x over x plus y, and we claim that V has a beta distribution with parameters alpha and beta. Before you go on, you should make sure that you fully understand the statement of the lemma, all the definitions, the terms involved, and therefore that you understand what we need to show in order to prove this lemma. We need to compute the density of V and check that it does have the density that this beta distribution has. Okay, that's what we need to do. And we know the densities of X and Y, which are gamma with given parameters. Okay, so we are going to use the results we studied for functions of random vectors. But if you recall, we only had a formula when the function mapped d-dimensional Euclidean space to d-dimensional Euclidean space. You couldn't change the dimension. So here we have a two-dimensional random vector, x and y, and we are mapping them to the one-dimensional vector v. So we can't directly use the formula. So what do? We get around it by introducing an extra random variable, which we are not interested in, but which will help us express this as a map from 2 to 2 dimensions. Okay, so that's what I'm saying here. So this map changes dimension, so we cannot directly use the formula. So we'll need to introduce an auxiliary random variable. And let's just take W to be X. There are other choices which will work as well. This is just one, it's somewhat arbitrary, but we'll take W to be X. Okay, so then VW is this function G of XY, which is defined in this way. The first coordinate is X over X plus Y, that's V. And the second coordinate is X, and that's supposed to represent W. Okay, so we have random variables X and Y with some joint distribution. We want to compute the joint distribution of VW, which are some function of XY. Okay, so let's start by thinking about where these random variables live. X and Y are gamma random variables, so they are non-negative. So this ratio is going to be non-negative as well, and it's going to lie between 0 and 1. Right? So V is going to lie between 0 and 1. W is just X, so it's going to be non-negative. That's all. Okay, so in order to use the formula, we need to find for a given V and W, we need to find all the X and Y that get mapped to them. So we want to find all solutions of this equation. And you can check quite easily from the definition. You can solve explicitly and you can check there's only one solution. which is to take x to be w because w was x, and y turns out to be this when you solve. Okay, it's w times 1 minus v over v, and that's the unique solution. Okay, the formula says sum over all possible solutions, the density at xy divided by the absolute value of the determinant of the Jacobian. Now, what's the joint density of x and y? These are gamma random variables, and moreover, we assume they are independent. So the joint density is the product of the individual densities. So x is gamma of alpha, so you get x to the alpha minus 1. And y is similarly, y has parameter beta, so it's y to the beta minus 1. The scale parameters are all 1, so the lambda disappears. We just get e to the minus x minus y, and this is the normalization constant to make it a density. I've just written the gamma densities and multiplied them out. So we are going to use this formula for which we have to compute the Jacobian of G at xy, and the Jacobian, just by calculating partial derivatives, turns out to be this matrix. And so when you calculate the determinant, you just get, okay, this term gives 0, you get x over x plus y squared. Substitute that in, substitute what x and y are in terms of v and w, and with a bit of manipulation, you'll get this expression. So the joint density of v and w is given by this complicated looking expression. Fine. Okay, what did we set out to calculate? We didn't care about W, we only cared about V. We want to know the density of V. How do we calculate the marginal density for V from the joint density for V and W? Okay, you get it by integrating out W, right? So the density at V, if you think of it as probability, this is the joint probability of the random variables V and W, taking the values little v and little w. You only care about the probability V takes the value little v, so you have to sum over all possible values of little w. So that's the law of total probability. Now it's a density, and instead of summing, you have to integrate. Okay, I'm just saying all that. So to get the marginal density of V, you have to integrate out over W. So the marginal density of V is the joint density integrated over all possible values of W, which is not to infinity. Okay, lot of algebra here. We are integrating out over W. I'm pulling out, what do I want to do? We get e raised to minus W over V. So I'm going to express everything here as W over V as much as possible. So I get W over V here. I have just a W to the alpha minus 1. So I'm going to write that as W over V to the alpha minus 1 times V to the alpha minus 1. Okay, I pull out all the terms that only depend on V from outside the integral. So I get V to the alpha minus 1, 1 minus V to the beta minus 1, and we get these constants that don't depend on W. And then what's left is the integral over W, W over V to the alpha minus 1. And from inside here, W over V to the beta minus 1. And we have an extra factor of W over V here, which kills off a 1. So that's this term here, e to the minus W over V dW. I had a V squared. I have an extra factor of V sticking around, which I stick under here. Okay, it's a bit messy, but this is what you get. And now we make a change of variables. So we call W over V, we call that U. So then U also runs between naught and infinity. The first term is U to the alpha plus beta minus 1. You have e to the minus U. And U is W over V, so du is dW over V. Remember, V is fixed. We are only integrating over W. Okay, so this V is fixed. Okay, so we get all this, and now you recognize this as the gamma integral. So this is just gamma to the alpha plus beta. Sorry, gamma of alpha plus beta over gamma alpha gamma beta. That's what you get. And then you have all these V terms, which I've rewritten here. So after all the calculation, the density of V is given by this. And now we recognize that this is the beta distribution with parameters alpha and beta. And so we are done. Okay, so that's the proof of the lemma. Okay, good. So why did we go through all this? So why do we care about beta random variables? We care about it because they are a very good choice of prior distribution for the kind of problem we are interested in, where our observables are Bernoulli random variables. So we'll come to that next. So that's the relevance of beta distributions. We are going to use them as priors for the unknown parameters mu I of the Bernoulli reward distributions. And it turns out that this choice is convenient because if we take the prior to have a beta distribution, then the posterior distribution is also beta. And this is rather special. We could have started with any arbitrary prior distribution we like. And we can always calculate the posterior distribution. In principle, there's no problem with that. Okay, so if we had started with something else, something arbitrary, we might still have been able to do this calculation in principle, but it gets messy in practice. After one step, after two steps, it's messier, and you have to keep doing it repeatedly as you for your sampling procedure for your multi-arm banded problem. As you have more and more observations, you have to keep recalculating the posterior, and the expressions can get incredibly complicated. So in practice, it's not feasible if you just choose some arbitrary prior distribution. Whereas if you start with the beta, it stays beta, only the parameters change, and they change in a way that's very easy to keep track of. So the calculations become feasible. Okay, so we are going to state this as our next lemma. Okay, so what does this say? It says that if X is a Bernoulli mu random variable, and we don't know mu, we assume that it has a prior distribution, a beta with parameters alpha and beta. That's our prior distribution for mu. Notice that mu is a probability. It's a number between 0 and 1, and beta distributions are conveniently supported on this interval. So it is indeed meaningful to choose a beta as a prior for this. It would not be meaningful to choose a normal distribution because if your normal distribution has the value -3 or even +1.5, they can't possibly be the parameter of a Bernoulli. Okay, beta works at least, which is a sanity check. And what does this lemma claim? The lemma claims that the posterior distribution of mu, if you observe a 1, is also beta. The 1 gets added to the alpha parameter, the beta parameter remains unchanged. Whereas if you observe a 0, a reward of 0, then it's still a beta distribution. The alpha parameter remains unchanged, and the beta increases by 1. So you can think of alpha as counting the successes and beta as counting the failures, and you update them So your prior says that it's as if you are starting with alpha successes and beta failures before you observed anything. You are pretending to have observed this many successes and failures. And then as you observe more, you are your posterior distribution gets updated appropriately, but remains a beta distribution. Okay, and you can see how convenient this expression is if it's true. Okay, so we have to prove this is true. Again, as usual, I'll emphasize that before starting to prove a lemma or a theorem, you should make sure you completely understand the statement. So do pause the recording here, make sure you understand the statement. Okay, so a prior distribution with this property that the posterior lies in the same family is called a conjugate prior. And those of you who are doing the unit on Bayesian statistics will no doubt have seen several examples of conjugate priors. Okay, and what this lemma says is that beta distributions are conjugate priors for Bernoulli random variables. Okay, so let's turn to the proof. Let's denote the density of mu by f sub mu. And the assumption is that if you evaluate that this density is that of a beta distribution, so if you evaluate it at p, you get p to the alpha minus 1 times 1 minus p to the beta minus 1, where alpha and beta are the parameters of your beta distribution, and all these things are the normalization constant to make it a density, to make it integrate to 1 over the interval not 1. Okay. Okay. So that's our prior. And moreover, if I tell you that mu has the value p, then x is Bernoulli mu, so you know that x takes the value 1 with probability p, it takes the value 0 with probability 1 minus p. So this is the conditional distribution of x given a value for mu. X here is the reward on the arm. Okay, what do we want to do? We want to calculate the posterior distribution for mu. And for that, we are going to use Bayes' formula. If you think of this as a probability, then the probability that mu takes the value p, you know how to apply Bayes' formula. You apply it in a very similar way for the density. So the posterior density is proportional to the prior density times the likelihood of observing 1 given p. Okay, and you have a similar thing if x took the value 0, but let's focus on the case where we are conditioning on x equals 1. So the posterior density of p at x equals 1 is proportional to the product of the prior and the likelihood. It's equal to this product divided by the integral of that thing. But rather than calculate the integral, I'm going to just say we know this has to be a density. So I'll calculate the proportionality constant by saying this has to integrate to 1. Okay. Here I've just substituted. So I've taken the density f mu of p here. I've dropped these constants as well for convenience. So I have p to the alpha minus 1, 1 minus p to the beta minus 1, and I'm multiplying it by p. The probability x equals 1 given p is p. I'm multiplying it by p, so that cancels the minus 1 next to the alpha. Okay, so that's why we get this. So the conditional density of mu evaluated at p, conditional on x equals 1, is proportional to this. The proportionality constant should be such as to make this integrate to 1. Okay, so what is that proportionality constant? If you look at this density, hopefully you recognize it. Take a moment to see if you recognize it. Okay, so you should recognize this as the density of a beta distribution with parameters alpha plus 1 and beta. Okay, and you know what constants you need for that beta distribution. So it's gamma of alpha plus beta plus 1 over gamma of alpha plus 1 gamma beta. I've not written it there. But anyway, once you plug in the constants, you recognize it as the density of this random variable. And that's what we needed to prove. That if the prior is beta alpha beta and we observe a 1, the posterior adds a 1 to the alpha. Okay, and you can do a similar calculation if x equals 0, which has probability 1 minus p. So the prior density gets multiplied by 1 minus p. And if you do the calculations, you will see that you end up with the density of a beta distribution with parameters alpha and beta plus 1. So you are adding 1 to the failures here. Okay, so that proves the lemma. So that proves the property that beta distributions are conjugate for Bernoulli observations. And that's a very important property of the beta distribution. Okay, so that was a lot of preliminaries, and these are all the preliminaries we needed to precisely state the Thompson sampling algorithm. So now I'm going to state the algorithm. So we have a multi-arm bandit with k independent Bernoulli arms, and the rewards are Bernoulli distributions with these unknown parameters mu1 through mu k. Okay. I'm going to assume independent beta priors for each of the arms. I could have chosen any parameters alpha and beta I like, but we are going to choose 1, 1. This was also what Thompson chose. Your answer shouldn't be too sensitive to this so long as the parameters you choose are small, but 1 is a common choice. So we'll choose this as the prior. Okay, and at the start of any round T, let's say we have already calculated the posterior distributions up to that time. So that's okay, or the corresponding prior distribution at the start of round T. So we sample mu hat 1 through mu hat k from the prior at the start of this round. Meaning we simulate random samples from these distributions independently. And you'll get some numbers. You'll get some numbers between 0 and 1. And then we are going to play the arm with the largest sample value, whichever of these happen to be the biggest. Okay, so the index of the arm we play is the value of I, which had the biggest mu hat I. I've written in to make this most general, so you might have ties. Two arms might get the same sample value, in which case you have to break the tie and it can be broken arbitrarily. But in fact, these are continuous distributions, so the probability of a tie is 0 and we don't care about that anyway. Okay, so that's the algorithm so far. So that's how you sample, how you decide which arm to play. And once you play this arm, you observe a reward on this arm. And based on that reward, you can compute the posterior. It's very easy. You just add 1 to either the first parameter of the beta if it's a success, or to the second parameter of the beta if it's a failure, if the reward was 0. Okay, so you update the posterior for the arm played. For all the other arms, you didn't observe the rewards, so you have no more information. There's nothing to update. You just stick with the prior. You gained no information. So your posterior distribution for the other arms is the same as the prior distribution. Okay, so you started round T with some priors. You've calculated the posteriors at the end of the round, and they only changed for the arm which was played. And you're going to set the priors at the start of round T plus 1 to be the posteriors at the end of round T. And that's the natural thing to do. Okay, and then you repeat this process indefinitely. That's the algorithm that tells you how to play this multi-arm bandit problem in perpetuity. There's no endpoint for the multi-arm bandit problems we are looking at. We play them until time infinity, and this fully specifies how it should be played. This is the Thompson sampling algorithm. Okay, I hope it's completely clear. Do take your time to make sure you fully understand how this algorithm works. And next week, we are going to analyze how well it does, how its regret behaves in a similar way to how we analyzed the performance of the UCB algorithm last week. Okay, I'll stop sharing my screen, and that's the end of today's lecture, which finished by presenting the Thompson sampling algorithm after all the preliminaries about beta and gamma distributions.